So this document has to be the structural engineer who's designing it, he has to be very well versed with this document. Moving on. Yeah, so one of the things, since we are dealing with the foundation design, so one of the things that you require is a soil bore log. So soil boring is a practice of geotechnical investigation. Its purpose is to determine the soil's load bearing capacities, what it so a bore log is typically used to provide key pieces of information, which is like what is the bearing capacity of the soil, the type of soil, is it a cohesive soil, is it a clay soil, a silty soil, sand. It will tell you about the water layer, it will tell you about the consistency of the soil, where is the rock, where should be your founding level. It will basically give you an idea of the lithology. So in the right hand side, you see a photo, which is basically a bore log, practical. And the one below is the report, the bore log report. So basically, this will give us an idea about the strata, which is below the pier. So based on this, you are going to set the safe bearing capacity, modulus of submarine reaction, and all the constants that you are going to need. You'll be finding from the lithology. So moving on. So before we are embarking upon the design, you need to know what are the materials that you're going to use. So you'll create a materials table, or you'll have it for your reference, and you'll include this in your design report. So it will basically tell you. Yeah. Am I audible, Naveen?
Yes, sir.
Yes, you are audible, sir.
All right. Thank you. So the materials table will basically tell you what is, as of now, you see, if you see over here, it is basically more of a concrete grade table. So it will basically tell you what is the grade of the material that you're going to use, what is the density, what are some other characteristics of these materials. So moving, if you see in the table, there's a PSC box. It is specifying the concrete grade. It is specifying the concrete grade. So this tells me that my PSC box girder, which I'm putting on both sides of my pier, is having a grade of M45. The density of the concrete that I'm using is 25. So maybe in the DBR, they will say, okay, no, just take, take 26, take 24, whatever. They might change it a bit. Or they might also specify, okay, for PSC box, you'd have to use 30, M30, use M30. So the DBR has to specify this. If not, then the designer, the detailed designer on his own capacity has to suggest it. And after a discussion with him, after approval from him, yeah, they can reach on what sort of values he can take. So the pedestals are the ones over here. The pedestals, seismic pedestals, bearing pedestals, all these are the pedestals. So pedestals, what is the grade? So I'm just taking a sample example and telling you what would be the most likely value, so that you can have an idea as to what would be the normal range. Seismic pedestals, M60, pier cap, foundations, M40, reinforcement, and what is the soil bearing capacity that we're using. Okay. So this materials table will help you to find out the characteristics of the material that you're using, and later on it will help you for the density values will help you for the self weight. So now, coming to one of the most important aspects, levels. So basically, the foundation design that we are going to discuss, it is not so different from the RCC footing design examples that we have solved in the RCC subject in our engineering. It is almost the same. The steps are the same, only some additional checks are required. But the main thing that separates the design of a bridge foundation is the lever arm. So what is the lever arm? You might have seen, you might have had some idea about it in your RCC and your mechanics subjects, that the lever arm is the distance which when multiplied with the force will give you the value of the moment. So considering that fact, it is very imperative for us to understand the different levels in order to come to the conclusion of what would be our moment. So when we are talking about levels, in front of you, there are different sorts of levels that I've marked on the sketch. Not all of these levels are important, but these levels should be at hand to the structural engineer when he's doing it. So basically, over here, there is a multi-cell box girder upon a pier, so which is giving you an idea of what are the different levels that you should be having in order to properly assess which force has to have what sort of lever arm, and it is being applied at what location. So if I start from the top, the center of bogey, you can say the centroid of the bogey. So basically, one would say that why would you need the level of the centroid of the bogey, right? So when we are calculating the wind load, the wind will apply on three different places. If we had a train bogey over here, the wind would apply on the train bogey, the wind would apply on the box girder, and the wind would apply or impose itself on the pier cap. So when we are trying to actuate the value of the wind moment that is acting on account of being imposed upon the center of the bogey, the centroid of the bogey plays a crucial role. So without this level, you will never know what would be the lever arm to be considered for the wind load that is acting upon the bogey. Okay. Similarly, top of rail. A few moments back, we just saw that was RTL. This is rail top level. So rail top level is basically this. There's the rail, the exact top portion of the rail. This is indicated by the RTL level. There's another level which is important, which is top of deck. Then the centroid of the girder, the top of bearings, top of pedestals, top of pier cap, centroid of the pier cap, somewhere over here, top of the pier. So over here, regardless of the fact that this actually looks like a homogeneous one single structure, in many cases, what would happen is you would actually have an RCC pier, but it would be complemented by a post-tension pier cap. So there has to be a level wherein the pier is cut off. So this is that level. So from this level on, and from this level above, there's the pier cap. This is where the pier cap stops, and this is where the pier cap starts. Okay. There's also high flood level and low flood level, but this is only used for locations wherein it is anticipated that there's going to be a flood, or there's some water body around, or there's the possibility of the bridge getting flooded. In the bottom portion, there's this low flood level, centroid of the vehicle. Now you would imagine that what is the centroid of the vehicle to what has the centroid of a vehicle to be doing on the pier. But just imagine if this pier is in between two highways, and by some accident, by some means, a vehicle crashes on the pier. So the centroid of the vehicle is that level as per the code, which is basically specifying at what point would the force of the impacting vehicle be acting upon the pier. So this would give you a very important information regarding what sort of vibrations, what sort of impact load that you have to consider, and at what portion. This is the top of pile cap. If we have pile caps, then if you're designing a pile foundation, then this level is very important. Bottom of pile cap and the pile cutoff level. Pile cutoff level is basically that point at which the pile is going to stop. Okay. So this was just a quick glimpse of the levels. So once you know these sort of levels are important, what you'll basically do is you'll create a table in Excel, and you'll start to input the values in that table. Okay. So once you have these values with you, and many times if you know the dimensions of certain components, you can directly have that table with you. So if you have this table, which is a very important tool for you, you can directly use this table, and as a reference, you can add up your values to create the lever arms for your movements. Okay, so you'll be creating a level table before you start calculating the moments. Now, so basic considerations for design in terms of loads, they're not too many. They're basically vertical loads, horizontal loads, longitudinal moments, and transverse moments. So longitudinal moments are moments around the, like for example, if I place this portion, for example, if I mark this line as the y-axis, and I mark this of my portion as the x-axis, so the moment which are acting around the x-axis, they are called as the longitudinal moment. The moments which are acting along the y-axis, they are the transverse moments. So basically, as I had discussed, like if you have an unequal span on both sides, you'll have a residual longitudinal moment with you. All right. And the types of loads, there are many types of loads, but for the sake of the webinar, I'm going to only discuss a few. So the main types of loads are the dead loads, the superimposed dead loads, and the live loads. There's also wind load, water current loads, and there are some other loads which I'll be discussing. But the main effort and the governing loads, the governing combinations for your design, they'll always come from usually the dead loads, the SIDL, and the live loads. So because these three types of loads, they represent such a colossal value of loads that are imparted upon the structure that most of the governing cases have to be dealing with these three kinds of loads. There's some additional forces, like as I just mentioned, vehicle collision load. Okay, like in case any vehicle comes, and just imagine it's a fully loaded truck and it is running at 150 kilometers per hour and it is hitting a pier directly. So it would be possible that if the pier is not designed for this impact load, it would fail. Okay, there are launcher loads, which I'll discuss later. The centrifugal forces, which I told you that if at all the span has a curvature, and as it is directly, the force is directly proportional to the curvature. So if you have got a very high, very sharp curvature, you will end up with a very high centrifugal force, and accordingly you'll have to give appropriate banking. Okay. There are temperature loads, creep and shrinkage due to prolonged durations, earthquake loads, and there's LWR. LWR is usually long welded rail. It is a part of the fixed superimposed dead load, which is basically the long welded rail, the rail which is spanning all the different viaducts.